Okay, welcome back. Now that we have the law of cosines, we're going to see it in action. We're going to use it to solve some triangles. So, example, solve the triangle with capital A equals 34.2 degrees, little b equals 17.3, little c equals 19.8. So to solve a triangle means to find out everything there is to know about the triangle. What are all the angles? What are all the sides? What color is it? Where is it from? What does it eat for breakfast? Okay, not those things, but all the sides and all the angles. When we know all of that, we will have solved the triangle. Remember, capital letters stand for angles. We have one of those, and lowercase letters stand for sides. We have two of those. And that's enough to determine a triangle, but still have to figure out the rest of what's going on with this triangle. Now, why can't we use the law of sines here? Well, the law of sines involves putting together one of the sides in its opposite angle with a different side in its opposite angle. But here, we don't have like two of the same letter. We have three different letters, so we can't set things up with the law of sines. But we can, as you probably guessed, use the law of cosines. We are going to use the one that has a capital A in it because we have angle A, and that looks like this. Little a squared, which we don't know, but this will let us figure it out, equals little b squared plus little c squared minus 2 times little b times little c times cosine of capital A. So we plug in the numbers we're given, and it looks like this. A squared equals 17.3 squared plus 19.8 squared minus 2 times 17.3 times 19.8 times the cosine of 34.2 degrees. Put all that into your calculator. Comes out to be 124.71 and so on. So that's a squared. So then a would be the square root of that number, which comes out as 11.1675261 about 11.2 if we round it to one place after the decimal point. So we got our number for little a. It's 11. Now that we have a little a and a capital A to go with it, now we can use the law of sines from here on out. So set it up with the number we found for little a was 11.2 over the sine of capital A, 34.2 degrees, equals the number we have for little b, 17.3, over the sine of capital B, which this will enable us to find. So we do our solving thing, cross multiply, work out. B turns out to be 60.3 degrees. Okay, we've got everything except one thing, and that is capital C. There's two ways we could figure out what capital C is. Probably the easiest way is once we've got two angles of a triangle, subtract from 180 degrees to get the third angle. So if we do that, C is 180 minus 34.2 minus 60.3, which is 85.5 degrees. The other way we could have done it would be to set up this sort of law of sines thing, but with a little c and a capital C, and work out from that what angle C is. So if we did that, we'd have 11.2 over the sine of 34.2 degrees equals 19.8 over the sine of C. Then go through and the procedure for solving this to work out what C is, and we get C equals 83.5 degrees. Uh-oh, wait a minute. That's close to what we got the other way, but it's not quite the same. One way we got C equals 85.5 degrees. The other way we got C equals 83.5 degrees. Did we make a mistake somewhere? Well, not really. The reason these are different is this number that we were using, 11.2, was not the exact value we got for little a. The exact value we got was, remember, 11.167526614, and there were really more digits after that, but that's what my calculator showed me. But we rounded it to 11.2. So when we use that rounded off version, we got some round off error. And that was enough to make a noticeable difference in the numbers we were getting for angle C. Just by rounding from 11.1 something to 11.2 made a difference in the ones digit of this angle answer. If we went back and used the non-rounded version, worked through the same problem, but instead of using 11.2 as the value for little a, we used 11.167526614, and then work through the same process of solving for b, we get that b is, and my calculator gave me 60.5450670 degrees. And then c, subtracting from 180, 180 minus 34.2 minus 60.5450670 is 85.25493297. If we use the law of sines directly on C, we would get that C is 85.254933233325. It still isn't quite the same because we still did a little bit of rounding. The exact value of A actually has more digits after this, but we came pretty close. It's 85.2549 something. So the reason I'm showing you this, the point of this example, is that you got to watch out for what happens when you round and then you deal with sines or cosines, because just because you have one number rounded, say, to the nearest tenth, if you work with that number and then somewhere along the line you take a sine or a cosine or an arc sine or an arc cosine of that number to get your final answer is not guaranteed to be accurate to the nearest tenth. You may be off more than that. So if accuracy is important to you, if it's important to be accurate to a certain number of decimal places, you got to keep that in mind and keep as much accuracy as you can in your intermediate calculations. Now, I know you're saying, okay, so if we put down the way you had it first, the like 85.5 or the 83.5, would we be wrong? Would you mark it wrong? And no, I wouldn't, unless I specifically said you need a certain number of decimal places of accuracy. If I did say that, then yeah, if you didn't have that much accuracy, I might take off a point or half a point. But best practice is, if you can, use like all the accuracy your calculator gives you. You might store that number in memory and bring it up. If you round it, it's close enough for most purposes. And I won't mark it wrong, but that is something you have to watch out for when you're rounding. Okay, on to the next example. Solve the triangle with little a equals 11, little b equals 13, little c equals 15. So here we have three sides of a triangle. And that means we need to find all three angles. So we can start with the law of cosines, and this time the numbers we have are the little a and the little b and the little c. We can plug all of those in. And the unknown that we have left to solve for is the capital A. So if we algebraically rearrange things and solve for the cosine of A, here's what that looks like. Now, you could have gotten it the way I did by using this version of the law of cosines, plugging in your numbers, and then doing some algebra to solve that equation for cosine A, or you could have just directly gone to one of those versions of the law of cosines that did have the cosine of A by itself on one side. Then you just plug in the numbers and this is what you're looking at. So when you calculate this out, this 13 squared plus 15 squared minus 11 squared divided by 2 times 13 times 15 comes out to be 0.7. Wouldn't hurt for you to try doing that yourself on your own calculator. Make sure you're putting that in correctly. And then A would be the arc cosine of 0.7, which is about 45.57 degrees. Once we have a big A and a little a together, now we can turn to the law of sines, which is a little simpler to use than the law of cosine. So when we can use it, we might as well. And if we fill in little a over the sine of big A equals little b over the sine of big B, we can solve to find what big B is. Turns out to be 57.56 degrees. And then once we have A and B, the easiest way to get angle C is 180 minus 45.57 minus 57.56 gives us 76.87 degrees. So now we have all three angles. We started all three sides. We have solved the triangle. Now, what about this example, which is almost like the last one? I've just changed one of the numbers. Solve the triangle with A equals 11, B equals 3, and C equals 15. So the only difference is now B is 3 instead of 13. Probably works the same way, right? Let's go ahead and do what we did last time. Almost exactly the same. And we get the cosine of A this time is 1.255 and so on. But that's impossible. Cosine can never be greater than 1. If you try asking your calculator for the arc cosine of 1.255, it'll give you an error message. So there is no triangle with these three sides. And actually, I could have predicted that because A and B together only add up to 14, whereas C is 15. So if one side of the triangle is 15 units long, the other two sides together would have to add up to more than that. They can't be less than 15 because the shortest distance between 2 points is a straight line. We can't have a shorter distance by going alongside A and then alongside B than we do going directly alongside C. In fact, that's sometimes called the triangle inequality. In any triangle, the length of any two sides added together is always greater than or equal to the third side, or the one side is always less than or equal to the other two added together. Here, that's not true, so this is not really a triangle. Okay, end of that example. I'm going to end this video right here, and in the next part, I'll come back and look at some other related things that kind of go along in this section. We'll see a formula for calculating the area of a triangle if you know the three sides, but nothing about the angles. And we'll look at one or two applications or word problems. See you then.